In this video, I'd like to keep working through our example to show how a neural network can compute complex nonlinear hypotheses. In the last video, we saw how a neural network can be used to compute the functions x1 and x2 and the function x1 or x2 when x1 and x2 are binary, that is, when they take on values in 0, 1. We can also have a network to compute negation, that is, to compute the function not x1. Let me just write down the weights associated with this network. We have only one input feature, x1 in this case, and a bias unit plus 1. And if I associate this with the weights plus 10 and minus 20, then my hypothesis is computing this. H of x equals sigmoid of 10 minus 20 times x1. So when x1 is equal to 0, my hypothesis would be computing g of 10 minus 20 times 0, which is just 10. And so that's approximately 1. And when x is equal to 1, this would be g of minus 10, which is therefore approximately equal to 0. And if you look at what these values are, that's essentially the not x1 function. So to include negations, the general idea is to put a large negative weight in front of the variable you want to negate. So if there's minus 20 multiplied by x1, and that's the general idea of how you end up negating x1. And so in an example that I hope you really figure out yourself, if you want to compute a function like this, not x1 and not x2, well, part of that would probably be putting large negative weights in front of x1 and x2, but it should be feasible to get a neural network with just one output unit to compute this as well. Right? And so this logical function not x1 and not x2 is going to be equal to 1 if and only if x1 equals x2 equals 0, right? So this is a logical function that says not x1, that means x1 must be 0, and not x2, that means x2 must be equal to 0 as well. So this logical function is equal to 1 if and only if both x1 and x2 are equal to 0. And hopefully you should be able to figure out how to make a small neural network to compute this logical function as well. Now, taking the three pieces that we have put together, that is the network for computing x1 and x2, and the network for computing not x1 and not x2, and one last network for computing x1 or x2, we should be able to put these three pieces together to compute this x1, x0, x2 function. And just to remind you, if this was x1, x2, this function that we want to compute would have negative examples here and here, and we'd have positive examples there and there. And so clearly this will need a nonlinear decision boundary in order to separate the positive and negative examples. Let's draw the network. I'm going to take my input plus 1, x1, x2, and create my first hidden unit here. I'm going to call this A21 because that's my first hidden unit. And I'm going to copy the weights over from the red network, the x1 and x2 networks. And I have minus 30, 20, 20. Next, let me create a second hidden unit, which I'm going to call A22. That is the second hidden unit of layer 2. And I'm going to copy over the cyan network in the middle. So I have the weights 10, minus 20, minus 20. And so let's fill in some of the truth table values. For the red network, we know that was computing the x1 and x2. And so this will be approximately 0, 0, 0, 1, depending on the values of x1 and x2. And for A22, that's the cyan network, well, we know the function not x1 and not x2, that outputs 1, 0, 0, 0 for the four values of x1 and x2. Finally, I'm going to create my output node, my output unit, that is A31. This is what will output h of x. And I'm going to copy over the OR network for that. And I'm going to need a plus 1 bias unit here, so I draw that in. And I'm going to copy over the weights from the green network, so that's minus 10, 20, 20. And we know earlier that this computes the OR function. So let's fill in the truth table entries. For the first entry is 0 or 1, which is going to be 1. Then next 0 or 0, which is 0, 0 or 0, which is 0, 1 or 0, and that falls to 1. And thus, h of x is equal to 1 when either both x1 and x2 are 0, or when x1 and x2 are both 1. And concretely, h of x outputs 1 exactly at these two locations, and it outputs 0 otherwise. And thus, with this neural network, which has an input layer, one hidden layer, and one output layer, we end up with a nonlinear decision boundary that computes this XNOR function. And the more general intuition is that in the input layer, we just had our raw inputs. Then we had our hidden layer, which computed some slightly more complex functions of the inputs that is shown here. It's slightly more complex functions. And then by adding yet another layer, we end up with an even more complex nonlinear function. And this is the sort of intuition about why neural networks can compute pretty complicated functions. That when you have multiple layers, you have a relatively simple function of the input to the second layer, but the third layer can build on that to compute even more complex functions, and then the layer after that can compute even more complex functions. To wrap up this video, I want to show you a fun example of an application of a neural network that captures this intuition of the deeper layers computing more complex features. I want to show you a video that I got from a good friend of mine, Jan LeCun. Jan is a professor at New York University at NYU, and he was one of the early pioneers of neural network research and is sort of a legend in the field now, and his ideas are used in sort of all sorts of products and applications throughout the world now. So I want to show you a video from some of his early work in which he was using a neural network to recognize handwriting, to do handwritten digit recognition. You might remember early in this class, at the start of this class, I said that one of the early successes of neural networks was trying to use it to read zip codes to help to help us send mail along, so we read postal codes. So this is one of the attempts. This is one of the algorithms used to try to address that problem. In the video that I'll show you, this area here is the input area that shows a handwritten character shown to the network. This column here shows a visualization of the features computed by sort of the first hidden layer of the network. And so the first hidden layer, this visualization shows different features, different edges and lines and so on detected. This is a visualization of the next hidden layer. It's kind of harder to see, kind of hard to understand the deeper hidden layers, and that's a visualization of what the next hidden layer is computing. You probably have a hard time seeing what's going on, much beyond the first hidden layer. But then finally, all of these learned features get fed to the output layer, and shown over here is the final answer, is the final predicted value for what handwritten digit the neural network thinks that is being shown. So let's take a look at the video. So I hope you enjoyed the video, and that this hopefully gave you some intuition about the sorts of pretty complicated functions neural networks can learn, in which it takes as input this image, just takes as input the raw pixels, and the first inner layer computes some set of features, the next inner layer computes even more complex features and even more complex features, and these features can then be used by essentially the final layer of logistic regression classifiers to make accurate predictions about what are the numbers that the network sees.